This is a little segment that I call Thumb Wars. And last week or last lectures, we were looking at atmospheric pressure and the magnitude of the atmospheric pressure and creating a vacuum with those suction cups and how strong the atmospheric pressure can be. We also calculated foot pressure, and we did conversions from English to metric and metric to English. So this week we're going to be looking at what's called hydraulic pressure. And so what I wanted to show you is it's very similar to the concept of Bernoulli's principle with the toothpaste. Now, hopefully this will stay in view. What I'm going to do is I'm going to push on one end, and the pressure is going to be equally transmitted, and it's going to be applied on the other end. And I can push on the other side as well. Now, if I were to apply equally on both sides with the same amount of force, this would be a kind of like a tug of war or a thumb war going back and forth. My left hand would probably lose because it's a little bit strong or a little bit weaker. The right hand would win because it's a little bit stronger, since that's the dominant hand. Okay, but what happens when we have a slightly different system and we have two different sides of these pistons, the syringes? So what's going to happen? If you were to choose a side, which side would you want to choose? You'd probably want to choose the larger one because you'd think that you'd be able to apply more force because it's a larger syringe, a larger piston. But I'm going to apply equally on both sides, and actually my left hand, which is the weaker, is actually winning. So how can this smaller one be applying a larger force? Well, let's bring in an even bigger one right here. And what I'm going to do is I'm going to push in on the larger end, and you'll see the smaller end being pushed out. I'm going to apply with a very, very small force. Actually, I'm applying a very large force, and it's moving very, very slowly. If I go over here, you can see that I can push this end in quite rapidly. What's the fastest that I can push it in the other side? Oh, that's the fastest it can go. This side goes in faster. I apply a force over here, and it comes out a lot more slowly. So let's take a look at the mathematics and what is happening with all of this. I got water all over the place. So this is hydraulic pressure, and if you can draw a system of if you can imagine the old dentist chairs where you'd have to press on this pedal to lift it up, or even the principle of a jack, where you are positioning the jack underneath the car and you're lifting the car up with your own force. So we're going to draw these round pistons that have the capacity to move up and down. And this is going to be a smaller one over here, and it's going to be connected to a larger one on the other side. So here's the larger one over here, and they're going to be connected from one side to the other through this point. So here's the smaller one, here's the larger one over here. And again, these have the pistons inside the syringes can move up and down, so I'm just going to draw those as well. So it's very similar to the syringes, except here's a smaller and here is a larger one over here. But they're both connected to each other. And we have a fluid, like water, that is connecting everything. So when I apply pressure on one side, it's going to be equally distributed all over the place. So if you remember that the formula for pressure is equal to force over area. So let's apply that to the left-hand side and the right-hand side. So we have the pressure on side 1 is going to be equal to the force on side 1 over the area of side 1. And the area is going to be this area that's pushing down, or this area on the other side pushing down or up. On the other side, we have the pressure for side 2, which is the larger, is going to be equal to the force over the area. And as we discussed Pascal's principle with the tube of toothpaste, when you apply a force, that force is going to be evenly distributed throughout the fluid. So what's going to happen is the P1, the pressure on this side, the water pressure, is going to be equal to the water pressure on the other side. The water pressures are going to be equal. So if P1 equals P2, we can take this and set it equal to this. So we have the force of 1 over the area of 1 will equal the force of 2 over the area of 2. So let's take it from the perspective of the smaller one. This is the force that is going to be coming in from the smaller one. So here's the smaller one, here's the larger one. I'm putting in this force on the left-hand side, and it's going to be pushing it over here on the other side. So here's going to be the force that's going to be coming out. We want to try to calculate what is the force coming out, and that is going to be this right here. So that's what we're trying to find. What is the force that's coming out on the other side? Let's just go ahead and rewrite this, and we're going to rearrange this. This is kind of our master formula for hydraulic pressure. So F1 over A1 equals F2 over A2. We want to solve for F2. So we're going to multiply both sides by A2. Multiply this side by A2. So let me write it over here. The force that's going to be coming out is going to be equal to, I'm going to write this first, the input force. So the force coming out is going to be equal to your input force times the area of 2 over the area of 1. Well, what is the area of 2 compared to the area of 1? The area of 2 is larger than the area of area 1. So your output force is going to be equal to whatever input force multiplied by a larger over a smaller. That means your F2, and here's the summary of all of this, your F2 is going to be larger. So in those old chairs where you can, maybe the old barber chairs or dentist chairs where they're pushing their foot down on this button or lever, they're applying a small force, but it's generating a large output force. Very similar with a jack and lifting a car. You're applying a small force and you're lifting a car with that. So how can we get a larger force by applying a smaller force? Well, let's go back to the concept of work. And work is going to be equal to force times distance. So work is equal to force times distance. Let's put this over here as well. Work equals force times distance. Here's my work in, and here's my work out. Earlier in the year, we talked about that with a machine, your work in is going to be equal to your work out. We can't get any more work out than what we put in. However, what's happening is we have a larger output force. So we have a very large output force over here. Here we have a small input force. Well, in this case, our work in is going to be equal to our work out. And if the work in is going to be equal to the work out, and these are going to be equal to each other, if I'm having a large force, this must move what distance? It must move a small distance. If this has the same work and a small force, it must move a larger distance. So going back to our summary, F2 is larger. However, it doesn't move as much. But doesn't move as much. So I want to show you again with the two pistons that I have here. Okay, I'm going to, and this is going to be what we're going to be seeing in the lab coming up. So I'm right about 15. We're taking it, let's see, actually it's going to be 15, 14, 13. We're at about 13 over here. And we're going to try to push this out. This is the 3 milliliters. How much do I have to push this in, to push this a distance way over here? So I'm going to push this until it reaches the 3 milliliters. Okay, so that moved the whole distance right there. And this moved from 13 to 12, while this moved all the way out to 3. So this moves quite a bit. This doesn't move as much. If I push this back in, we can see how much that this is going to be moving. It doesn't really move much, the distance. So yeah, in terms of volume, it didn't look like that it moved that much. But in terms of distance, it moves even less because it's a larger area. So the distance that the smaller piston moves is a lot more, and I can apply a smaller force to create a larger force with hydraulic pressure, but to counter that, it's not going to be moving very much. So the force, the output force is larger, but it does not move as much.